Hey guys, my name is Walter Ketchum. I am a nursing student at the University of Arkansas Fayetteville, and I'm going to be talking to you today about Klein bottles. Klein bottles are pretty cool, or at least in my mind they are. Here's what they look like. Um, yeah, they can be made out of glass, rubber, or I've even seen them like plastic too. But yep, it's got one. The opening of the bottle is at the bottom, which is really weird to me anyway. But yep, and they come in a loop, and you can fill. It's really hard to fill them up, but you can still fill them up, as you can see on the right picture. And these are like so. These are more intricate Klein bottles. They're still Klein bottles, but these are more like artistic kind of renditions of like Klein bottles. They still work, but like it'd be really, really hard to actually fill these ones up because there's so much that you have to like air versus water. You'd have to get by vapor pressure. There we go. Okay, so what is a Klein bottle? A Klein bottle is a bottle that represents what would happen if we stitched two Mobius loops together. And what Mobius loops are, I'll get into that later. But when we do this, when we stitch them together, we create an object that encompasses itself. So it has also no edges, no boundaries, and is non-orientable. And what this means is that if something has no edges, well, then it never, inside to the outside, never ends. And yeah, so like the inside and the outside of the bottle are the same thing. You can basically like take a pen and like walk across the entire like entirety of the bottle inside of it and through it, and you will still like it's infinite. Um, what Klein bottles are really is they're like a kind of a 3D rendition of a 4D bottle or 4D Klein bottle. So since true Klein bottles are 4D, they cannot exist in our three-dimensional plane since we live there. And so, no matter how we try as we may, we cannot create a true Klein bottle. Klein bottles we know and we can touch are only representations, like I said, are only representations of the true thing. And if that kind of confuses you a little bit, I can explain a little bit better. So let's say this ball, it's three-dimensional, right? And so if I take a picture of the ball, then it becomes two-dimensional because that picture that I took of this ball that's 3D is going to be a representation of the 3D object. And so that's kind of how Klein bottles are. They exist as kind of like a representation of what a Klein bottle would be if it could exist in our three-dimensional plane. So Mobius loops, as you'll recall, like a minute ago, what a Klein bottle is it's kind of like a stitched, like two of these things stitched together. So Mobius loops are loops that are one-sided and one-edged. For a visual, take a piece of paper and you can twist it. I can't really do it with this one. There we go. You can twist it and then combine them together, and what you'll get is kind of a weird little loop thing going on. Not really malleable, this paper, so sorry. But yeah, kind of looks like that. And that loop is non-orientable and basically infinite. So I thought of an example a minute ago of this, but like, let's say we were an ant and we walked across a Mobius loop. I can show you what it looks like real quick. It looks like that. That's what a true Mobius loop looks like. And so if you can imagine yourself as an ant, you can crawl along that Mobius loop. Doesn't matter if it's on the outside or inside, you will eventually get back to the inside and then back to the outside. And you'll keep going, and it's basically infinite. Yeah. Whereas like a regular loop, like a cylinder, almost, not a cylinder, excuse me. If you put two loops together, it'll be a cylinder. But basically, like with a regular loop, you'll just be walking either on the outside or the inside. There's no way to get to either one from just walking it. From just walking it, excuse me. Okay, that's what it looks like again. The thinking behind the Klein bottle. So basically, there was a German mathematician named Felix Klein, and he was thinking about loops one day. He knew that if you take a rectangle and you piece together the ends of it, you will create a cylinder. Using that logic, he wanted to know what would happen if you take two twisted Mobius loops, so two Mobius loops, and stitch them together, would it make a cylinder? And he did so, and he created a Klein bottle. So who was Felix? Who is this Felix Klein? Well, like I said earlier, he was a German mathematician, and he found it, or theorized it, I guess, excuse me, in 1882. And like I said earlier, he wanted to take two Mobius loops, sew them together, and create a bottle with no boundaries and no defined, inside or outside, which to me is mind-boggling that anybody could even think or even theorize something like this. But I guess mathematicians are a different breed entirely. Can you fill a Klein bottle? Yes, but it's very difficult. It is a little difficult since the liquid is vapor locked. And so what vapor locked is it's that the liquid has to fight against the pressure from the vapors, the air that's in the Klein bottle, to move or escape. And so in order to fill it, you have to beat the vapor lock. And so how I've found to do this, or other people have found to do this, is basically like submerge the Klein bottle and like kind of move it around and kind of force those little air bubbles out of there. And so because of the conservation of mass, that little bit of air bubble is going to be the exact same amount of water that's going to go into it eventually. And so after a while of filling that up, after a while of doing that, you'll fill it up eventually. And so in regular containers, we can think of this in another way. So in regular containers, like a measuring cup, have to rely on gravity to hold the liquid because, well, don't have a cup here. I have a cup, yeah, right. So basically, if I pour water into this cup, gravity's holding it in there. So if I do this, the water's going to come out, right? So with the Klein bottle, gravity is helping it along a little bit, but not really because you got to fight pressure still, water pressure and the vapor lock from the outside. And so you just kind of like orientate it to get the air to water out, excuse me. But the thing with Klein bottles, filling them up, is that you're not going to ever get that tiny bit of water out of it. So there's always going to be some amount of water once you fill it up. Okay, so here are the formulas to make a Klein bottle. When I look at these, I have no idea what I'm really looking at because, well, I haven't studied. I'm not going to be a math educator or somebody who's going to use this type of math a lot. And so I do know cosine, sine, square root, and all that. But yeah, I used to have a graphing calculator that could do this. But yeah, but it's really cool that somebody like that I can get a hold of like this information, like how to like the formula to like graph one anyway, x, y, and z axes. Excuse me. So what is the practical use of the Klein bottle? Well, in a branch of mathematics called topography, we use Klein bottles as an example of an object that is non-orientable. So this means that the object cannot be orientated or reflected and still look the same. Topography, that little branch of mathematics that we use Klein bottles as an example in, is a study of surfaces, mostly land surfaces. And so we use topography in like maps and things like that. So when I think of topography graphs, topography as a branch of mathematics, I think of a map. So these topography maps, what they do is they show the surface of an area of Earth. So like, let's say the Rocky Mountains, it's going to show you the elevation, kind of a 3D a little bit. If you get the 3D version of like a topography map, you can see kind of like how high something is by like color coded, and that's pretty cool. But if you're just 2D, then it'll have like different areas will be like color coded and stuff like that. And yeah, basically like according to sea level and elevation, it shows you basically a good idea of what how elevated a landmass might be. All right, thank you guys so much for watching this video. Hope y'all have a great rest of y'all's week.